Look, Cog, look. Did you know that CO2 comes out of our campfires? That's a tasty marshmallow treat, but a porcupine might prefer to eat the juicy inner bark of the stick. People can't digest the inner bark of a tree, but we can still get energy from it by burning it. Firewood is made from a few different kinds of carbon-based molecules, but we're going to simplify and focus on cellulose. Cellulose is the most abundant carbohydrate on Earth. That's because plant cells are making it to strengthen their cell walls. Let's take a look. This plant cell has a vacuole that stores water, food, or waste. It's got a nucleus with genetic material in it. It's got some other important organelles, but we're going to focus on that remarkably strong cell wall. See all these fibers laid down all cattywampus like a pick-up sticks game? Those are cellulose fibers. Each cellulose fiber is made of microfibers. Each microfiber is made of cellulose molecules, and each cellulose molecule is just a very long chain of glucose molecules. Thousands of glucose molecules in each chain. Cellulose is in the cell walls of grasses, bamboo, wood, cactus, leaves, and, well, pretty much all plants. Special gut microbes in herbivores' digestive tract can break down cellulose molecules. Humans don't have those microbes. We can't break cellulose down into pieces that go through the cellular respiration pathway to make chemical energy. It's not food for us, like the carbs we talked about in episode 2 are. People do need cellulose fibers to keep their waste moving along, though, if you know what I'm talking about. But we can't get energy from it unless we use it to make fire. There are lots of ways to start a fire, but fire is dangerous and gets out of control quickly. So don't try any fire building without adult supervision. I'll supervise you, Cog. Imagine you've been given some sticks. If you can use them to make fire, you'll win a tasty prize. Behind each of these 4 curtains is a fire-making strategy. Which curtain will you choose? I see you've chose curtain 4. First, let's see what you didn't choose. Behind curtain 1 is friction. Rubbing sticks together is back-breaking work. Behind curtain 2 is a spark or a flame. That's easy with a lighter, but you would have had to use flint and steel. It takes practice to learn how to do that. Behind curtain 3, focusing energy from the sun with a magnifying glass. That takes too long. Now, what could be behind your curtain? Better take a closer look, Cog. Oh, it's lightning. Lucky you. It's not backbreaking, doesn't take any practice, and it's instantaneous. And look, you made fire. Your prize is a run-over breakfast burrito. You can warm it over the fire you made. To start a fire, you need to complete the fire triangle. You need fuel, oxygen, and heat from friction, sparks, a flame, focused sunlight, or lightning. The fire will burn until it runs out of fuel, oxygen, or heat. Did you think your fire was burning sticks, Cog? If so, you thought wrong. Heat starts the fire by exciting atoms of carbon, oxygen, and hydrogen in cellulose. Those atoms escape into the air and form light gases. It's those light gases that burn when they mix with oxygen. See what's produced? Carbon dioxide, water, light, and heat. Let's see it. This stick is our fuel. Oxygen is in the air. This match is our heat source. The blue flame at the bottom shows us where the oxygen enters and mixes with the light gases. The yellow and orange flames are free-floating carbon atoms, hot enough to glow. Now what's left is glowing embers. Pure carbon left in the stick is mixing with oxygen to make CO2, heat, and light. You could say that cellulose puts carbon in your fire's carbon dioxide. Here are 3 ways cellulose puts carbon in CO2. Microbes inside the digestive tract of an herbivore can break cellulose down into glucose molecules that are delivered to the cells and go through cellular respiration to make CO2, water, and chemical energy for the herbivore. Microbes, either in the poop or in the environment, can break down the cellulose into glucose molecules that go through cellular respiration to make carbon dioxide, water, and chemical energy for the microbes. That's decomposition. Or cellulose can be broken down by fire to produce CO2, water, heat, and light. But here's the thing. The cellulose in all these scenarios came from plants that were recently alive. Whether they were digested, decomposed, or burned, the CO2 produced from that cellulose can be taken back up by plants to grow and reproduce, returning it to our web of life. So let's recap. Cellulose is a very long chain of glucose molecules made by plants to build strong cell walls. We can't digest it to turn it into chemical energy, but we can burn it to get heat and light. A fire needs fuel, oxygen, and a heat source to burn. Campfires burn indirectly as light gases escape from the cellulose and mix with oxygen in the air. Fire produces carbon dioxide, water vapor, heat, and light. Cellulose can be digested, decomposed, or burned. These processes produce CO2, water, and energy. The CO2 can be taken up by trees and other plants, returned to our living web of life. No, we're not done learning about sources of CO2. For instance, did you know CO2 comes out of our... Yes, I know, Cog. That's 3 times. I won't use that gag again.